Okay, so first of all, big thank you to the organizers for inviting me to give this talk. And so today I will try to convince you that tidal effects are some kind of a window to understand various aspects of gravity. And of course, tidal effects are probably one of the oldest, phenomena which have been studied from even the 16th century or so. And there are various fascinating things about tidal effects, like these are some things that we observe in day-to-day life, like high tides, low tides, which affect oceans. And there are also various physical effects like tidal locking of the moon and the earth slowing down due to the moon and things like that, which have been very well studied in the literature. But what I will try to tell you is that there are probably a few things which still require further studies, and how tidal effects can be a very useful thing in many other ways, like constraining modified theories of gravity and things like that. And so the outline of the talk is the following. So first I will talk about tidal effects. I have said time independent. I mean, these are really not time independent, but the point is that we will ignore any small dependence of time. And then we will talk about tidal disruptions near black holes and wormholes, and I will try to show you how very classical result, rather a Newtonian result, gets modified in the presence of GR, and how, because we know that in near wormholes the energy conditions, some of the energy conditions may not be satisfied. So when you talk about tidal disruptions, because the black hole has an event horizon and the wormhole has a throat, there is a qualitative difference about on how these geometries will interact with objects close to them. Then I will talk about how tidal effects can be actually used to constrain a class of modified gravity theories, the so-called beyond Hondesky class of theories. And then I will go to how the more recent works, like about stellar dynamics and tidal effects. And I will talk about, for example, asymmetric tidal disruptions, which are not very well known or not very well studied, and try to convince you that these might give observable signatures which can be used to at least study stellar dynamics, not so much stellar properties, but stellar dynamics. And then I will end with a summary of the talk of the things. So these are roughly the references that I base this talk on, and of course, I mean the references included within these things, they are the previous works, and these are the collaborators: Pritam Devojyoti, Shashwato Rajibul, Dhananjay Rohan, and Ishan Jain. And so let me start. So as I told you, tidal effects, they are one of the most fascinating features of non-local gravity, of course. I mean, the basic thing about tidal interactions, tidal forces, that these are non-local manifestations of gravity, and these can tear apart a massive object when non-local forces exceed the force of self-gravity. They can be torn apart by these tidal forces, and they can produce observable luminous flares. And and tidal forces are known to be one of the main physical processes in the formation of accretion disks around black holes. And to give you a very familiar example, in July of 1992, the comet Shoemaker-Levy, it broke up into, I think, 22 or 24 pieces due to the tidal forces of Jupiter, and collided with the Jupiter surface. So here there is an image of this, of this breakup. You can see this whole line of, small objects which have been actually, it's a part of the big object, the comet Shoemaker-Levy, which has been torn apart by the tidal force of Jupiter, and they sort of went and hit Jupiter and produced and produced huge impacts on the surface of Jupiter, and these were very well documented by the then available technologies, and this is a very well-known example of what a tidal effect can do to a stellar object. And of course, you know that when a star, I mean, this is the comet, so when a star gets ripped apart due to the tidal forces, one can, in principle, get a fascinating view of the interior, because the exterior is just stripped out. So one can get a fascinating view of the interior, which is crucial to understanding stellar composition and stellar evolution. And these are all very well known. And what is more recent are, is this fact that tidal forces can actually provide, they can tell you, they can give a basis for astrophysical tests of some gravity beyond GR. Well, the basic reason is that tidal forces and stellar equilibrium, they depend on the pressure balance equation inside a star. And when you go to theories of gravity beyond the Einstein-Hilbert theory, it often happens that the low energy limit of such a theory modifies the pressure balance equation. Well, there is a lot of more story which I will come when I go to, but in the sense that it has been realized in the last maybe 7 or 8 years that the low energy limit of modified gravity, a class of modified gravities, they actually leave some imprint on the matter, forming an overdense region or a stellar object, for example. And so if that happens, then the pressure balance equation, being one of the most crucial ingredients in understanding many properties of stellar structure, like luminosity and things like that, there is immediately some effect which actually can be constrained. And one possible way to constrain it, which I will talk about, is the tidal effects. And there are of course many other ways of constraining using other astrophysical probes of such modified gravity theories, but my talk will only focus on the tidal effects. And of course, when you talk about tidal effects, the analytical computations are never easy, because this is a sample which is generated from our code, which shows the tidal disruption, which shows at least a partial tidal disruption. And you see that a star which was a perfectly well-defined spherical object, this is what happens to it. I mean, there is a core and there are two asymmetric tails, and there is a central black hole in this region, and this is how the thing behaves. And of course, you can therefore see that there is pretty much no hope of doing any analytical computations over here, and one has to resort to full-fledged numerical techniques. But even those numerical techniques are not so easy, in the sense that there are various competing forces, and one needs a very high power computer or supercomputer to compute such effects, and that is something that we will talk about. So this is the broad introduction to what I am going to tell you about tidal effects. And so let's just get into a little more details. And so this is what I teach my first year undergraduates, that so when you have the Earth, which is a spherical shape, assume it to be a spherical shape, and the Moon, then you could compute tidal effects by simply doing a Taylor series expansion of this quantity. And I have marked 4 points, A, B, C, and this is, well, don't bother about this, C and D are symmetric. So if you compute the acceleration at A, okay, then essentially it is like gm by r minus delta r squared minus, so this delta r is the radius of the Earth. So I've called it as delta r because it's very small compared to the center of mass distance between the Earth and the Moon. And if you do that, then you find that at the point A, there is an effective force, there is an effective acceleration which actually goes as 1 over r cubed. Okay, so that is the hallmark of tidal interactions, that the interaction, the acceleration due to this non-local process, it goes as 1 over r cubed rather than a 1 over r squared. And this is in the direction of I cap, and here I have given you the what is the directions of I cap and j cap. And if you compute that at B, this is a minus I cap. So essentially there is a stretching effect in the xy direction. And similarly in the x direction, sorry. Similarly in the y direction, if you compute, okay, so there will be some forces towards the center at this point C, and forces towards the center at this point at this lower point, and these are these basically act towards the center of the Earth, and these are the this is the high tide region and this is the low tide region, and the oceans will actually bulge or compress due to these effects, and this is what usually happens. And as I told you that I consider this as a time independent situation, but of course there is much more dynamics to it. Both bodies are spinning, and there's a rotation of the moon, but this is the snapshot picture which sort of tells you the basic effect that the tidal force goes as 1 over an r cube, and there is a bulge and there is a compression on these two sides. Okay. So now, what we do is now, I mean, having said this, and we sort of want to understand this in terms of in terms of general relativity, which is what we are interested in. And so in GR you want to consider non-local effects, and non-local effects we know from the Einstein's equivalence principle that non-local effects of GR essentially mean that inhomogeneous gravity, it cannot be eliminated in a freely falling frame, because when a frame is freely falling there will be apparent forces because both of them are being attracted towards the center of the Earth, and the relative movement of a collection of nearby massive particles which are moving in an arbitrary gravitational background is defined, is described by the so-called the geodesic deviation equation, where this is the 4 vector u mu and this r is the Riemann tensor and this xi is basically the deviation vector. And if you have under non-relativistic weak curvature limit, you define this tangent vector 1 0 0 0, and you end up getting this d2 xi dt squared is equal to the second derivative of phi, where the Newtonian gravitational potential phi is defined from g naught naught is minus of 1 plus 2 phi. And what you now need to do is to understand how this works for an extended object. Okay, so these are basically geodesics which correspond to point particles, and if you want to go to extended objects, if you want to study extended objects, then you need to define locally flat coordinates. If you need to define a tetrad basis which is locally flat all over the geodesic, and such a tetrad basis is called it's called the Fermi normal frame. And because what we finally want to do is, I have a star and this star is falling under non-local gravity, it's moving under non-local gravity. The star by itself has some hydrodynamics, okay, and maybe Euler's equation, Poisson's equation, whatever. Now the thing is, I want to treat the star as a Newtonian object, because otherwise things get very messy, okay, and I need to treat the star as a Newtonian object. So when the star is going in a geodesic, assuming that the size of the star is much smaller than the size of the central object, I need a locally flat frame at each point on its geodesic. Otherwise I will not be able to apply the Newtonian hydrodynamics to the star, right? So that is why I need the Fermi normal frame, and this Fermi normal frame is characterized by the fact that it's locally flat everywhere on the geodesic. So there is the time-like geodesic G, and everywhere if you take the metric tensor, then the projection of the metric tensor is basically the flat metric everywhere, and the Christoffel connection is 0. But of course the derivative of the Christoffel connection may not be 0, so the Riemann tensor remains non-zero, and essentially the idea is that the basis vectors are parallelly transported all over the geodesic. Okay, so these details can be found in this famous paper by Manasse and Missner way back in 1963. So the strategy that we would follow is that for a generic stationary space-time, so this is not static, I'm just graduating one step beyond, so I have a generic stationary space-time, I construct the Fermi normal coordinates, there is a very standard way of constructing these coordinates. And then I consider equatorial, parabolic or elliptical orbits. And because remember that here we are really bound by the fact that there's an analytical computation, and I need to choose an orbit over which hydrodynamic equilibrium is, at each point of time I require hydrodynamic equilibrium in the star. And so we consider some given orbit, maybe a equatorial, if you are in Schwarzschild background, okay, the equatorial plane is good enough. So you consider the equatorial, parabolic or elliptical orbit by suitably choosing energy and angular momentum. Then you solve the hydrodynamic equation of the fluid star numerically in the presence of the tidal potential. So that's the only new thing which essentially comes in. But the concept over here is that the tidal potential, so that actually will add to the hydrodynamic equations, and then you obtain a critical density below which a star may be disrupted, and this will give you values of other critical parameters, like you can have a critical mass or a critical radius, and there are various stellar relations which you can then use in order to compute when the star is getting disrupted. But I must warn you that this is an equilibrium situation. So essentially what you do is first you compute the tidal potential. How do you compute the tidal potential? Well, as I told you, you go to the Fermi normal tetrad, you construct the Fermi normal tetrad, take the suitable projections, and then expand the background metric in terms of the Fermi normal coordinates like so, and then define these quantities like the 0, 0 component you want, and the tidal, because the tidal potential it's a Newtonian thing, it's like g naught naught plus 1, and this is effective because you are on the Fermi normal frame, you are in a locally flat basis, all through the geodesic, and then the phi tidal is computed. This was a prescription given by Ishii, Shibata, and Mino in 2005. You could compute the phi tidal. It's basically just a simple graduate level exercise, and you can compute this quantity, which is theseCij's will be the functions of the coordinates, and this is what you do. And once you do that, then you actually run through this algorithm, this whole strategy, and you can obtain the corresponding critical density and the critical parameters of the in the process. Okay. So if you consider the tidal potential in Fermi normal frame, then this is the same expression as in last slide that I have just written down again, and what you can show is that at least for spherically symmetric configurations, what you can show is that the first term in the tidal potential, that is your ubiquitous r cube term. So this is something that we had already seen, and I told you that when you do a very simple calculation, you see that the tidal potential, the tidal field actually, this basically goes as 1 over r cubed, and so there will be an r to the power 4 term, r to the power 5 terms, etc., etc. And I'm sorry, this is actually the addition. The first term was that r squared, which will give you the force as r cubed. Then this is the r, order 1 over r cubed, order 1 over r to the power 4, order 1 of r to the power 5, etc. And when a star comes near a black hole horizon or a wormhole throat, these third, fifth terms, etc., third, fourth, fifth terms, etc., they actually become significant. So the 1 over these terms over here, they bring in asymmetry in the deformed shape of the star. And here I've actually plotted the tidal potential as a function of on one plane as a function of the x coordinate. Okay, and you can already see that if you take the second order, and that's perfectly that's a symmetric thing, but third and fourth order, they deform the tidal potential in order to give you the the asymmetry in the shape of the star. So then this is a very small slide in which I will just tell you how to then go about the computation. You use Poisson's equation, the usual equations in your hydrodynamics, the Poisson's equation, the Euler equation, and very importantly over here I will use a polytropic star, a polytropic equation of state. So you may wonder whether this is generic enough. Well, the point is that the types of stars that I will study, okay, later on, they are all sort of nearby main sequence and convective stars. So polytropic equation of state would be good enough for them. And you know that when you have when you are in the Fermi normal coordinates, because of the parallel transport of the Fermi normal basis, that automatically brings in you know, a velocity field, a rotational velocity field, and then you know, this rotational velocity field we have to actually choose the star to be co-rotating so that it remains it remains static in the Fermi normal frame. This is a technical detail, but so the star will rotate in the Fermi normal frame, and the Fermi normal frame is also rotating, and this is the co-rotational frequency called as omega. And then you solve the fluid equations to obtain the density profile and when it experiences the tidal field, and this is a numerical procedure by which you solve all these equations together, and you iteratively do it until you reach an equilibrium configuration, and that equilibrium configuration gives you the final thing of the star. So this is one example. This is actually, you know, you find the minimum possible central density for which the star remains stable from getting tidally disrupted, and this limit is known as the Roche limit or the tidal disruption limit. And this is typically what happens. You know, you start with a perfectly spherically symmetric configuration, and in the tidal force field, what happens is that the star starts getting deformed and in asymmetrically in one direction. I mean, it is not that this side is completely spherical either. So, but the deformation is asymmetric. That is what I wanted to tell you. And you define some quantities like, you know, omega squared by rho critical, where rho critical is the the minimum possible critical density for which the star remains stable, and then you define stability criteria like, you know, if a star is going to be stable, then its you know, central density must be, then its density at some point r must be given, rather at the core C must be greater than the rho critical, and typically it is you know, we talk about it in these units. That is what astrophysicists do, and this is the epsilon gives another criteria, but that's okay. I mean, it's just a matter of detail. So with this, I will go to how we look at tidal disruptions near black holes and wormholes. And again, the textbook result for the tidal radius, that is the distance up to which a star can come without being tidally disrupted, this is given by what is known as the 1/3 law. How do you get the 1/3 law? Remember, I showed you that 1 over r cubed in the acceleration. Just equate it to the acceleration due to gravity at the surface of the star. Okay, it's a very, very crude type of approximation, but I tell you what, it works very well. So this 1/3 law is the Newtonian result, where you know the tidal acceleration on the surface, it goes as 1 over r cubed, and you know that you know what is the acceleration due to gravity, which quantifies self gravity at the surface. So when the tidal acceleration, so that acceleration due to gravity is gm by r squared, so r being the radius of the star. So when the self gravity cannot hold up anymore to the tidal effect, it will break apart, and that basically is that 1/3 because of that 1 over r cubed which came in the expression for the tidal force. And this is just a very, very crude approximation, and it's independent of any you know, any type of stellar properties, but it's usually taken as a standard working formula, and as I told you, it works actually quite well, as I'll tell you. And we studied how GR modifies this formula by going through this entire rigmarole about, you know, writing down the you know, numerical, rather writing down the hydrodynamic equations, solve them iteratively, this, that, so you do all these things, and you study to what extent, you know, I mean, to what extent this tidal potential is modified to a more generic formula like r tidal by r star, any dimensionless quantities, is alpha m by m star to the power beta, and we found that this beta, which is like 1/3 over here, it can maximally, you know, go up to 0.3 or 0.36. Okay, so that type of small deviation, but otherwise the Newtonian law works surprisingly and perfectly well, even for a very, very generic situation in which you do not have those crude approximations that I had used. So this also indicated to what extent wormholes can act as black hole mimickers, because remember that you know, Damour and Solodukhin in this famous paper in 2007, they showed that various properties of various observable properties of black holes are actually, you know, shared shared by the wormhole solutions as well. So, but what we saw was that because of this energy condition violations near the throat of the wormhole, so for the case of the I mean, that brings in the difference in that in the power law compared to black holes and wormholes. Actually, wormholes go one way and black holes go the other way. And the other thing we studied was the peak fallback rate of debris from a disrupted star. That's also significantly different between black holes and wormholes. And in order to do all this analysis, we considered a Schwarzschild geometry, a traversible wormhole of the Morris-Thorne type, which is given by this metric, and the exponential wormhole. Okay, and basically, I mean, then you construct the Fermi normal basis. Don't bother about the technical details, and this is basically the result. That if you now apply that the tidal disruption that alpha m by m star to the power beta, if you compute rho critical versus this RP is the periastron position, that is the position nearest approach of the stellar object near the black hole horizon or the wormhole throat, then the Newtonian result is over here, and as I told you, this is the rho critical. This rho critical for the wormhole actually lesser than the rho critical for the black hole, and this leads to various conclusions about when a star will actually be disrupted by a wormhole, or when it will be eaten alive, or when the same thing for the black hole as well. So what we found, as I told you, is that asymptotically this beta goes as 1/3. That's the Newtonian result, and this also is reflected in this plot as well. And for the Schwarzschild black holes, it turns out that beta is less than 1/3, but it's more like 0.3 or 0.301, something like that. For exponential black holes, we have beta greater than 1/3, but the deviation was also less than 10% of the original 1/3. And then we calculated the peak fallback rate, because after tidal disruption, what happens is that the tidal debris, it will actually try to, it's not instantaneously captured. So the center of mass follows the trajectory and the debris follows the center of mass. So after a while, the center of mass turns back, the debris falls back to the pericenter, and you can actually show that this has been calculated, I mean, these are approximations, approximate analysis of, the time, the minimum time required for the debris to come back to the pericenter, and what we found is that this peak fallback rate from our analysis is differed by about 4 times. That's not a lot, but at least there is some tangible difference in the peak fallback rate between the black hole and the wormhole. And now I come to constraining, how we can use tidal effects to constrain a class of modified gravity theories, and this is the beyond Einstein-Hilbert theories. And here you need to have the screening mechanism which are used to recover GR in the solar system scales, because these are very precisely determined. And one example is Weinstein screening, and which is actually followed in this beyond Horndeski theories. And what was discovered, quite surprisingly, is that this Weinstein mechanism is only partially effective in these beyond Horndeski theories. Inside sources, modifications are only partially suppressed, and a very nice discussion can be found in this paper by Koyama and Saxton. And at the end of the day, when the dust has settled, it points to the fact that the low energy limit, this yields a modified pressure balance equation that I was talking to you initially inside astrophysical objects, and these allow for astrophysical constraints on these beyond Horndeski theories, because these will carry these, the modified pressure balance equation carries the imprint of the modification to Einstein-Hilbert, and if you could constrain this by, oh my, I started late, isn't it? So, okay, fine, I'll try to. If you constrain this using the beyond Horndeski theories, then you would probably get an astrophysical constraint on such theories. So anyway, so I'll just skip these things, and because I just have 5 minutes left, I'll probably just go to the main thing. So the main thing, so in the last 5 minutes, what I will try to impress upon you is that, I mean, what I talked about till now, it was all static in the sense that there was no time dependence anywhere. And now I will, I want to understand the dynamics of the stellar disruption effects. And this disruption might be asymmetric, and it leads to important consequences. And these all have to be analyzed. Numerically. Forget about this. Okay, so this is how typical asymmetric stellar disruption, typical asymmetric tidal disruption looks like. You start with the spherical symmetry, then it starts getting deformed, there is more deformation, and there is a central object over here. It basically, some part gets detached and forms the usual thing about the accretion disk, and some part becomes unbounded, and finally you have a core left. So what I wanted to do is I wanted to show you a few representative situations in which okay. So let's first look at, so this is the result of the numerical code. Sorry. Okay. So this is this shows circularization of debris in the when a star has been completely disrupted. Okay. So the color coding is basically the log column density, which is essentially the the density, the integral of rho dz when you are looking directly at the star from the top. So this is basically what is called a circularization. The debris will actually, finally, I mean, we have not run the code for such a long time, but finally it will circularize. And let us look at the next one that I wanted to show you is a full symmetric tidal disruption. So here you have a star, and now this guy is coming out from here. Now look at what happens, and this is a close-up of this thing. And after a tidal disruption, it it sort of goes away. I mean, it becomes there is no core formation. I mean, there is no there is no central core over here, and so this will keep going, and finally it will disappear from the line of sight. Okay, and this is what happens. The third one is a partial symmetric disruption, and when you have a partial symmetric disruption, so here we had to use two color codings, because one is for this one and one is for the close-up that I have over here. See, in partial disruption, partial symmetric disruption, you see importantly the whole thing over here looks symmetric about a central axis. Okay, and that is something which is expected, because here what I've done is I've actually projected the star from a very, very long distance. But what is most important, that what is the essence of what I'm going to talk now, is asymmetric partial disruption. So just look at this thing carefully. I mean, there is this star which is coming, the central object. This is just a blob that we have this for representation. And now this starts getting asymmetrically asymmetrically disturbed, because one part of the tail becomes more prominent than the other part. And then what happens is finally this tail, I mean the tail near the black hole will start circularizing, like in the first video that I showed you, and one part of the tail will simply it sort of gets detached and moves away. Okay, and so here actually much of this tail has been swallowed up, and this tail is actually still moving away. And this is something new. This is something that has not been really studied too much. And so coming back. Oh no, just one second. Yeah. So coming back, what we have seen is that these are the parameters that I had used for partial disruption, for asymmetric partial disruption, etc. Now, the main thing that I would that I want to emphasize, again, I'll skip over all these results. Yeah. So look at this particular figure. So this is essentially, I have defined a quantity called beta, which is basically quantifies the distance from which the star is starting from the towards the black hole. And the more the beta, it actually comes closer to the black hole horizon, or to the wormhole throat, if you want it that way. So if you look at the maximum beta that we have, that is for the closest approach to the near the black hole horizon, you see this is basically the center of mass of the core. The center of mass of the core evolves in this way, and I showed you how the core is formed. And this deviates so much from what would happen if you would have taken the star to be a point mass which is moving under the influence of that same gravitational field. So because of this mass law, because of some mass has gone, and because there are many other things which are like, there is some energy loss, and some energy has been eaten up by the black hole, and because I started with a parabolic orbit whose specific energy was equal to 1, that is equal to c squared. Now the part which has been eaten up by the black hole actually goes into an elliptic orbit, and you know that the elliptic orbit has lesser energy than the parabolic orbit, and because of the asymmetry, okay, so center of mass, so the core energy changes, and what happens is that after some part of the mass has been disrupted, it starts falling back into the core and giving it a kick velocity, as they call it, and including everything, taking everything into account, this is basically the picture that emerges, that these huge deviations, and remember that this is actually in the xy coordinates, this is like almost 42 solar mass deviation between the solar radius deviation, sorry, between the what would happen with the tidal disruption and what would happen if there was just a point mass. So then I'll end with a summary that a star is tidally deformed in the presence of a tidal field, and we investigated the maximum deformation that it can achieve without getting tidally disrupted. The numerical analysis we performed in Fermi normal frame in which the star is considered, and we studied dependence of the tidal tail on the orbital inclination, which I have not really shown here, that we considered Kerr black holes, and for Kerr black holes, then if you go to some off the equatorial plane, then the analysis will change substantially, but that is something that I have not talked about here. Then I talked about the dependence of the tidal field for black holes and wormholes, where we showed how the thing deviates from the differences in the peak fallback rate, how the thing deviates from the Newtonian analysis. Then I told you how to put a parametric constraint on a class of modified gravity theories using this Roche lobe filling secondary stars. Unfortunately, I couldn't discuss it too much because of the time constraints. But then the last part, I told you about the numerical SPH, the smooth particle hydrodynamics code, which we developed to understand real-time dynamics of tidal disruptions. And then we focused on asymmetric disruptions, and then we found many novel results, including some considerations about energy and angular momentum carried by the core and the deviation of the core, etc. And what I want to emphasize is that now that we have this whole thing in place, so it's possible to model real-time asymmetric tidal disruptions in any situation, in the sense that for a wormhole, for a Kerr black hole, or even for modified theories of gravity, etc., etc. And the dynamics of such things actually should reveal many interesting features in the future, which I hope to come back again in the future. Thank you very much. Sorry, it was a bit rushed at the end, but I'll take questions.
Thank you, Professor Sarkar. An interesting talk, and it's a new area you are exploring. There is enough time to take some questions. Yeah, there I can see a hand there.
So thanks for showing those movies. I was just wondering if you knew what is the statistical proportions of each of these scenarios that you showed.
Right.
So which ones are most likely to be seen?
No. So these situations, actually, yeah, unfortunately, I had to skip. So I started with an initial configuration, you see.
Right, yeah.
So that initial configuration, I started with at some distance.
Right.
Okay, and it followed some Lane-Emden density profile, and so I fixed the mass. So the mass of the star was always 1 solar mass. Mm-hmm. The radius of the star is 1 solar radius, and I just fixed the distance from the central object and put it in a parabolic trajectory with a given eccentricity. Mm-hmm. So that is one star which is coming. So if you could take a statistical distribution of many stars which are randomly coming, that would give you actually the difference between the rate of tidal disruptions and the rate of and the difference with the I think when it is swallowed as a whole, that will possibly give you the number of events that you can see. So that analysis I have not done. This is only for a single star with a given mass, with a given radius, with a given eccentricity of the starting orbit, which is approaching that black hole.
I see. Okay. Thank you. Should I pass it here?
Yeah, so I had a very nice talk. So I had a question. So you said that the Weinstein screening inside of these stars,
right,
basically the condition breaks down so you can use it.
Right.
So what does that actually depend on? Does that depend on the interior density of the star? Like,
no,
would you
so-
see a similar thing in
Yeah,
galaxies
actually-
is what I'm trying to say.
So basically what happens is if you take the low energy limit
Yeah.
of these theories beyond Horndeski, and if you see that the Weinstein mechanism does not screen inside an overdense region fully. Okay, outside the overdense region is fine. So then, depending on the background, I mean, you take basically a cosmological background with some, you have the scalar fields, you fix some initial condition for the scalar field. And what happens is that in the low energy, in the low energy limit, there are additional terms which come with the pressure balance equation. So those will depend on what are the initial conditions that you have chosen. So essentially, the pressure balance equation like this dPdr, that is basically modified by terms which are proportional to the parameter of that beyond Horndeski theory.
Okay, well, ask.
Yeah.
So do you also consider the deformation of the central object itself?
No. Yeah, that's a very good question. Actually, what we did over here is, I have taken the star to be one solar mass, and what happens, well, is that I have gone down up to 10 to the power 3 solar mass central object. Okay, so we have studied from 10 to the power 6 up to 10 to the power 3. There should not be any significant deviation in the central mass. Even if it is there, it would be very small. That is the assumption we started with. We have not really taken back reaction into account. Now, what happens is that when you have these types of effects, there is a competition in the sense that if your star is of a large mass, then most probably it will not be tidally disrupted but eaten as a whole. Okay, and it also depends on what is the radius of closest approach. So there are two parameters over here, the mass ratio as we call it, and the tidal radius divided by the periastron radius, that is the position of the closest approach. So there are two competing factors. So what we find is that these deviations in trajectory that I showed you, these are maximal for the mass ratio of about 10 to the power minus 3, which corresponds to the intermediate mass black holes. So if you have a 1 solar mass star and let's say a 10 to the power 6 black hole, it's completely disrupted. Okay. If you have let's say a 10 to the power 3 solar mass star and a 10 to the power 4 black hole, 10 to the power 5 black hole, it's eaten up. So in this situation, we have a 1 solar mass and a 10 to the power 3 solar mass black hole. Here is where you see these interesting things about the deviation, because this is the scenario which allows for partial, asymmetric partial tidal disruptions. Okay, so this competition is very important, and yes, I have not really considered back reaction. I expect them to be small. Okay.
Yeah, very nice talk, Tapabrata. Actually, my question is a bit tangential to your talk. It's about compact binary coalescence.
Right.
Of course, we know that there is tidal disruption when you have a binary neutron star coalescence.
Right.
But my question is about binary black hole coalescence. So let's say similar mass black holes. I mean, does a space-time also call tidal disruption of another space-time of a similar character? That's the question that I would like to ask. It's a tangential question.
Yeah. So in principle, yes, I mean, they would be tidal encounters, but I won't know how to model them because, I mean, in the absence of any hydrodynamics. So the whole thing that I did was a hydrodynamic modeling, right? So in that case, I don't know, there might be very non-trivial changes in the background space-time itself. So I won't know how to answer that question. Right, back reactions.
It's not taken that account.
Yeah. Hi. Thanks for the very nice talk. I was wondering, in the first part, you fixed these alpha and beta parameters from in GR or alternate theories. Do you still use the same idea that surface gravity equal to tidal?
No.
Okay.
This is completely numerical. Okay. So what we did was, and this is actually a time-independent scenario. So what we did was we basically, solved this hydrodynamic equations, and then we came up with the formula ab initio. There was no assumption about that this thing. But what we found is that the Newtonian law is actually surprisingly good. I mean, the point.
Does this work also for your elliptical encounter? Parabolic encounters and time-dependent simulations? It does.
No. I mean, So here, what we have done is basically we have, This is not an equilibrium situation at all. So that was an equilibrium, right? I mean, there's this thing, the star is not really deformed. So you go up to the point where the Roche lobe starts overflowing, and then you stop over there. You say that, okay, this is my tidal disruption. So here we do not have that equilibrium. So here what we have is that you have basically, you start the star with a Lane-Emden profile, and there are geodesic there are gravity forces which are acting, which you could actually either approximate by some potential, but we use the full GR, the geodesic result. On top of that, there is self-gravity. On top of that, there is the hydrodynamics, you have artificial viscosity and things like that. So this is a completely non-equilibrium thing. So there, that 1/3 will not really have any meaning.
So just a one-word question.
Yes,
to,
please, yeah.
So you mentioned wormholes.
Right.
What about tidal disruptions near gravis stars, dark energy
Yeah.
stars?
So what
Chaplin, Laughlin objects.
So what I'm telling you is that actually this code took us about 2 years to develop, but now that we have it, you give me a metric, a reasonable metric, I'll give you this picture for any sort of this thing, right? So it's a very general thing that we have.
Thank you, Professor Sarkar, again. So now we have